Okay, so good morning. Yesterday we briefly looked at multiplying radical expressions. Um, Today we're going to continue on with that, multiplying expressions with more than one term. That would be using the distributive property. And one of these things we're going to use today that's very important. It's in uh, question B here. We're going to kind of apply that to something else today. So in example A, we have 3 root 11 times 2 plus root 11. So what we would do is we would use the distributive property and multiply both terms by that sign. So 3 root 11 times 2 is actually pretty straightforward. It would just be multiply the 2 and the 3 to give us the 6. 3 root 11 times root 11 is actually interesting because what happens is when you multiply root 11 by root 11, you end up getting root 11 squared, which is just 11. Again, you can do most of this on your calculators. So this is actually pretty simple topic. Like for example, you can do 3 root 11 times 2 on your calculator to give you this, and then you can do 3 root 11 times 11, or root 11, to give you 33. So this is pretty straightforward. It gets a little more challenging when we start introducing A's and B's, which I'll show you in a minute. Now, yesterday I put a star by example B because actually, this isn't necessarily the example I was talking about, but we're going to look at multiplying things like this today. This is the double distributive. I can never say that word, double distributive property, meaning we're going to apply this twice. So I'm going to multiply the first term, root 5, by this guy and this guy. And then I'm going to multiply the 3 root 2 by this guy and this guy. So this is the distributive property twice. What this typically does is it creates 4 terms. And then we simplify radicals and combine any like radicals. So pretty straightforward. I mean, it's not much different than anything we were doing yesterday. And I think what I'm going to do in a minute, once I go through C, is show you a couple of these because it is quite simple. Question number C, same thing again. It's the double distributive property. So this guy gets multiplied by this guy and this guy. And then we do it again with the 7b. Again, you end up with 4 terms and you simplify. So let's do some. Again, you guys know I don't really like doing examples. I like to work through them with you. So let me just kind of look through. Okay, there's a lot of practice here, which is really good. So let's do a little mixture of review. We'll start with a simple one, and then we'll move into some harder ones. So for example, just to get you guys warmed up for this morning, something like question A. Well, what you do is you multiply anything outside the radical with anything outside the radical, and anything inside the radical with anything inside the radical. So what this becomes is just the cube root of 21. And I don't think we can simplify that. So that's it, cube root 21, right? Sorry, if you're wondering where I got the 21, it's just 7 times 3. Okay, pretty simple. But let's look at like something like question C, which is a little bit more difficult. So what I would do with question C is I would multiply the numbers outside the radicals. So it would be, hold on, there's a there was a hair on my screen. This would be 4 times 2. Okay, and then under my cube root, I would get 4 times 5. So I multiply the 4 and the 2 to give me 8. and I multiply the 4 times 5 to give me 20, and that's it, 8 root 20. I can't simplify that, I don't think, so that's it. Now, it becomes a little more difficult as we scroll down. So let's do a couple of some harder ones here. Like H would be a good example. And then I'm going to get you guys to actually practice a couple of these because it is really important to know how to do these. So let me just do H. And maybe I'll do J as well. And then I'm going to ask you guys to try a couple. So something like H. I'm going to use the double distributive property. Sorry, what I mean is not the double distributive property. I'm going to use the distributive property. That 3 root 5 gets multiplied by both terms. So 3 times 2 is 6. And then I'm going to get root 5 times 5. Okay, which, I mean, you don't need to write 5 times 5. You could write 25. I just want to show you where that comes from. Plus 12 root 5, 3 times 4, no problem there. But what's interesting about this is the square root of 5 times 5, you can do this on your calculator if you don't believe me, is just 5. So this would be 6 times 5 plus 12 root 5, or 30 plus 12 root 5. All right, there is a reason I'm showing you this because of kind of like the next topic. We're going to look at something like J. Okay, so let me do J, and then I'll give you guys a minute or two to practice this. I guess I'll zoom out. I'll keep H on the screen. So J, what do I do with something like J? Well, I'm going to do the distributive property 2 times. So 8 root 7 times root 7. Okay, so that's easy. So let me do this one piece at a time. So I'm going to start with the first terms. 8 root 7 times 7. Okay, well, that's just 8 root 7 times 7, which is 49. Square root of 7 times 7 is 7. So I'm going to simplify that in a minute. Okay, what about the next term? 8 root 7 times 3 root 5. Okay, so 8 times 3 is 24. Root 7 times root 5 is 35. Okay, no problem there. Let's do the other terms. Oh, I got something in the chat here. Okay, negative root 5 times root 7. So this would be a negative root 35. And then I didn't really give myself enough room, did I? And then the last terms. So this would be another negative 3 root 5 times 5. Sorry, I ran out of room. Okay, now I simplify. So 8 times root 7 plus 7 is just going to be 8 times 7. 24 root 30. Actually, I can simplify this. So 24 root 35 minus 30 root 35. Again, don't cancel anything. You can't cancel. This is like saying 24x minus x. So this is going to be 23 root 35 minus 3 times 5. And then I can finally simplify this a little bit more because that 8 times the 7, I can combine with the 15. So this would be 56 plus 23 root 35 minus 15. And then finally, we would get 41 plus 23 root 35. Whew. Okay, now somebody in the chat just asked me if I could do G, which I can. G is pretty straightforward. The only challenge with G is simplifying it. So what we're doing with G is we're just multiplying all of this together. So cube root 4 times 2 times 54 is 400.
Mr.
Yes?
24 minus 1 minus 3 is it 19?
What?
18.
What about 18?
24 minus 1 minus 3 is 18.
Yeah, but why would you subtract the minus 3? It's not the same root sign.
Okay.
Right? I can only subtract if they're the exact same root sign. Okay? Okay, so number or letter G, 4 times 2 times 54 is 432. A squared times A squared, this would be A2. We would have 5 A's. And then B, we would have 1, 2, and another 5. Then you could simplify this. So so I need a perfect square. Let's see, a perfect square that goes into this one. So, okay, good. All right, so this is almost done. I just need to simplify it. So what I end up getting when I simplify this is, I'll get,
Teacher, should we simplify it?
sorry?
Should we simplify it or finish like this?
No, you're not finished. You have to simplify it.
Oh, okay.
So 3, I can remove a 16. That leaves me with 27. I can, oops, sorry, I didn't mean to write that down yet. I can remove 3 A's. We were doing this yesterday. I can remove B. And what that'll leave me with is 27A squared B squared. All right, so why don't you guys try a couple of these for practice? I didn't intend to do this many, but that's okay. So why don't you guys try, I'm trying to put as much on the screen as I can. Why don't you guys try I and L? You don't have to worry about K, but try I and L. All right, and I'll be back in a minute. We'll check your answers. Okay, let's look at the answers here. Somebody just asked me a question, said, Mr. Mark, in question J, where did I get -3 times 5? There was a bit of confusion about this earlier with another student asking me to combine all three of these terms. -3 times the square root of 5 times 5. What is the square root of 5 times 5? It is -3 times 5. The square root of 5 times 5 is 5. So that's where that came from. Okay. So -3 root x times x plus 7. All right. So again, distributive property here. Let me check the chat. Okay. So this would be -3 root x times x plus -21 root x. Now, here the square root of x times x is just x. So this would be -3x minus 21 root x, and that's it. I can't simplify that. I mean, I could factor out a 3, but it's not asking me to factor, so this is fine. Actually, it's asking me to do the opposite of factoring, really, if you think about it. Okay, so what about L? Okay, something like L. Let's see. We're going to do I can never say that word. The distributive property 2 times. I'm going to start. Let me zoom in too, so I can make sure I can fit it all in. I'm going to multiply these two terms. So I would get 11 times the square root of m times m. I'm going to do it again with the second one. So then I would add to that 11 times the square root of mn. I'm going to run out of room again, I bet. Then I'm going to do the inside terms. So I'm going to get 4 times the square root of m and n. And then the last one, I'm going to get 4 times the square root of n times n. I ran out of room just like last time, but that's okay. So now I'm going to simplify. So 11 times the square root of m times m is just 11m. Now, these two terms I can combine. 11 root mn and 4 root mn is like saying 11x plus 4x. So that's 15x, well, sorry, 15mn. And then I'm going to add to that my last term here, which is just 4n. And that's it. Halas, finished. Pretty straightforward. Well, not straightforward, a little bit annoying. There's some work to be done there, but it's not too bad. All right. So what's the point of this? Well, the whole point of this is to do something where it's called rationalizing the denominator. So there's some practice here. Guys, you can skip pages 32, 33, 34. You can skip pages 32.
This one cancel or what?
Yep, omit 32 to 36. We don't need it. And we're going to apply what we just learned to rationalizing the denominator. And this is something that'll come in handy in some future math courses. So rationalizing the denominator. So we will learn in this topic the final technique for simplifying a radical. Okay, so topic 21, we looked at simplifying a radical, and we kind of continued on through that through other topics. So what we're going to do is look at the last step or the last possible thing you could do to simplify a radical, and it's called rationalizing the denominator. This right here was topic 21. And what we're going to look at today, or right now, is the process of removing a radical from a denominator. So if you read about the simplified form of a radical, the radicand has no factor raised to a power greater than or equal to the index. What that means is the number in the root sign is reduced as small as possible. The radicand, so the number inside the radical, does not have a fraction. And number 3, there are no radicals in the denominator. Now, we didn't really talk about this back in topic number 1 because we weren't ready. But to finally simplify a radical, you must remove any radicals in the denominator. Now, remember, if you can't remember what a denominator is, it's always numerator over denominator. Okay, so you can't have a radical in the bottom of a fraction. So there's a problem with A, B, C, and D. And we're going to simplify this by multiplying the denominator by its, well, I want to say by itself. It's easier than it sounds. So we're going to look at 2 examples. We're going to look at one term, and then we're going to look at, and we'll practice that. The one term is quite easy, and then we'll look at 2 terms, which is very, you'll see this tomorrow. You'll see a question about this tomorrow. Yeah, tomorrow. So how do you do this? Well, what we're going to do to remove the radical from the denominator is we're going to multiply the equations by that radical that is in the denominator. It says right here, to rationalize the denominator, a square root of a perfect square is needed. So in each of these cases, in A, B, C, and D, you're going to multiply them by themselves. So I'm going to multiply A by root 3 over root 3. For B, I'm going to multiply it by root 7 over root 7. And you'll kind of see how this works. It's a lot easier than it sounds. So in A, if I have 6 root 3 and I multiply it by root 3 over root 3, that eliminates the square root or the radical in the denominator. Because like we just learned, square root of
So we want to remove the base?
Yes, you want to remove the radical in the denominator. Okay, so root 3 times root 3 is root 3 squared, which just simplifies to be 3. Now, it's not about removing the denominator. It's about removing the radical from the denominator. So in this example, we can simplify it and reduce it to lowest terms. But the student who just talked on the microphone, it's not about removing the denominator. It's about rationalizing the denominator, which means getting rid of the root sign. So if you look at number 7, number B, it's the square root, let me zoom in, the square root of y to the power of 5 and 7. So I want to simplify this. So first things first, I'm going to separate it into 2 radicals. So it's the same as root y5, root 7. And then, simplify it, but I need to get rid of this root 7. You can't have a radical in the denominator. So I multiply it by root 7 over root 7. Root 7 squared is 7. And I mean, that's it. It's pretty straightforward with one term. And of course, I'm going to practice this with you. Don't worry. Same thing for question C. I want to simplify the denominator, so I multiply the denominator by itself. The key here is you really want to make sure you multiply the top and the bottom by itself. and then simplify. This one's, so C has a little trick in it. I'm sorry, I was just reading this. C does have a little trick in it though. Because this is a cube root, you need to form a perfect cube to make that simplify, to get rid of the radical. So when they multiply this out, they only add 1 5, so we get 3 of these, and 2 s's, so we get 3 of these to make a perfect cube. This is what's called a perfect cube. On your tests and things like that, and on your assignments, you're mostly dealing with perfect squares. But if you did have a cube root, you wouldn't be making a perfect square, you'd be making a perfect cube. And when I take the cube root of that, it gets rid of the radical. So not too tricky, even if it is a cube root. And then finally, another one, it's just the same thing over and over. Let's just do some together. Okay, so let's start with an easy one. We'll look at some harder ones. Okay, so A, I need to get rid of root 3. So what I want to do, because this is a square root, I want to create a perfect square. So I'm going to multiply this by root 3 over root 3. Now that's just a 1, by the way. I'm not actually changing anything. But root 3 times root 3 ends up being just a 3. So what this simplifies to be is root 3 over 3. And if you don't believe me, I don't know why they give us so much room for this, but root 3 times 3 is root 9, which is 3. So that's where that 3 comes from up there. Again, this is the last step of simplifying a radical. Okay, let's look at a harder one, something like C here. I need to get rid of this radical in the denominator. Well, I'm going to multiply this by root 2y over root 2y. And this will leave me with 6 root 2y over 2y. And I'm almost done here. The only thing I need to do now is simplify this, because I can reduce that 6 and the 2. So this, for the final full answer, this would be 3 root 2y over y. All right, so let me just see. I want to see how hard they get. Okay, well, we'll worry about them in a minute. So how about you guys get warmed up and try B and D. So try these two. These will be good warm-ups, and then we'll look at some harder ones. All right, let's have a look at the answers here. So now for B, we can rewrite that as root 1 over root x. The next thing we're going to do is then get rid of that radical in the denominator. So I'm going to multiply that by root x over root x. And you end up getting the square root of x over x. You don't need to put the 1 in there. Okay, question D. I'm going to multiply that by root a over root a. So I end up getting negative 2a square root a over a. And I can reduce that. So I can reduce the a's. So I would get negative 2 root a. Ooh, that was a nice one. That one worked out to be real good. Okay, so let's look at some harder ones. Now, most of the time, well, I shouldn't say most of the time, on tests and assignments, it's mostly going to look like D or E or something where it's just a square root. But if you did have something like a cube root or a quarter root, you need to get rid of them somehow. So these examples like G and H aren't maybe the best examples for, say, your test tomorrow, but they're good practice. Like if I wanted to get rid of this number here, well, I'm going to need to create a perfect cube. So what I'm going to do is I'm going to multiply it by, root 3 4 squared over root 3 4 squared. Now, why did I pick 4 squared? Because that will create what's called a perfect cube. So I get 7 root 3. I don't know why I'm writing this so small. Zoom in a little bit over this. So what this ends up being is the cube root of 4 cubed, which is just 4. So 7, 3, 16 over 4. The big ones that you guys want to practice are the squares, but we can get rid of cube roots doing this. Okay. So there's lots of practice here. Let's do one more big one, and then that'll be it. Because like things like M and N are also good to look at. So let's do one of these as well. What one should I do? Well, let's do N. Okay, so N. I want to get rid of this root 24. Well, that's easy. Well, actually, first, let's see if I can simplify root 24. Before I do anything, I should try and simplify it. And root 24, I can actually simplify this before I do anything. So 7, this is, root 24 is the same as 2 root 6. So now that it's a little simplified, so I got 8 over 14 root 6. I can still keep simplifying this because I can reduce 8 over 14 to 4 over 7 root 6. I'm almost done. But now what I want to do is get rid of that root 6. So let me pick a different color here. I'm going to multiply that by root 6 over root 6. And that will leave me with 4 root 6 over 7 times 6. So 4 root 6 over 42. And we can still simplify this dividing by 2. Whew. That was a lot of work for such a simple little tiny question, but it was mostly just simplifying it, reducing fractions, nothing we haven't done in other topics. All right, cool. Now, So what would you do if you had two terms in the denominator? If you have two terms in the denominator, you need to do something a little different, and it's called multiplying it by the conjugate. So I'm going to show you this right now in a second, but if you did something like this, it would create a rational or a rationalized expression, an expression with no radicals in it. Basically what we were doing 10 minutes ago, foiling, first, outside, inside, last. Excuse me. So let's have a look at this. Simplify the expressions by rationalizing the denominator. So if you look at A and B have in the denominators two terms. So with two terms, what you need to do is multiply them by what's called their conjugate. Okay, we're going to multiply the numerator and denominator by the conjugate. So what is the conjugate? The conjugate is the two terms on the bottom, but with a different sign in the middle. These right here are what we call conjugates. So you'll notice that it's 2 plus root 6, and then we're going to multiply it by 2 minus root 6. Again, this is only when you have two terms in the denominator. So there's only two examples here. I'm going to show you these two, and then I'm going to get you to practice one. Probably practice something like maybe D or E. Yes.
So when in the test, when I see two terms, I will do like that.
Yep, exactly. So how do you do it? Well, I mean, we already know how to do it. It's just we have to apply what we've learned. So I see two terms here. I'm going to multiply it by what's called the conjugate. The number on the top gets multiplied by the same thing as well. So you multiply the numerator and the denominator and just apply your properties of multiplication that we've done so far. So the 2, for example, gets multiplied. This one down here, be very careful with. We're foiling it. We're double distributing it. So it ends up being, I don't know where to write this, but 2 times 2 is 4, so 2 squared. The reason we pick the conjugate is then we get a positive 2, 6 and a negative 2, 6, and they end up canceling. You'll see me when I do an example like this below. The last terms, root 6 times negative root 6, that's where this guy comes from. I mean, I hate doing these because they're already solved. There's like nothing for me to write. Same thing for this one. Two terms on the bottom. So you multiply the top and the bottom by the opposite, the conjugate, and simplify. So let's do some, because again, I hate doing the ones that are already done. Let's do some together. Okay, so question A, two terms on the bottom. That means what I'm going to need to do is multiply the top and the bottom by what's called the conjugate, or the opposite. So conjugate doesn't mean opposite. I think in like Latin, it kind of means like a partner or something, or a pair almost. But instead of root 2 plus 3, I'm going to multiply this by root 2 minus 3. All right, so that's I was going to say that's the hard part done, but now what I do is I simplify. So I would get 4 root 2 minus 12 over. So again, what I'm doing here is I'm multiplying the bottoms. So I get square root of 2 times 2. Okay, that's my first term. Then I'm going to get negative 3 root 2. Then I'm going to get positive 3 root 2. And the cool thing is they cancel. They always will cancel. That's the whole point of the conjugate. And then I'm going to add to this, or I guess subtract to this, a 3 squared. So what I end up getting is 4, whoops, that's not a 4. 4 root 2 minus 12 over square root of 2, or square root of 4 is 2 minus 9. Two minus 9 is a minus 7. And there you go. Now, some people put the negative on the top, but it doesn't really matter where you put it. Okay, so why don't you guys try this one?
Sir,
Yes?
from where we got minus 3 power 2?
Root 2 times minus 3.
Okay.
Mister,
Yeah.
root 2 multiply 2, then you write minus 3. Why you choose minus?
Someone literally just asked me that. Root 2, see what I'm circling, times minus 3.
Okay.
All right, so take a minute, try letter B or number B. Letter B, number B, same thing. Excuse me. Okay, so let's look at this answer here. All right, so same thing. I'm going to multiply this by root 6 plus 2. Because that's the conjugate. So what I end up getting is 8 root, oh, you know what I should do is hold on, let me pick a different color here so it doesn't blend in with A too much. So what I end up getting is 8 root 6 plus 2 times 8, which is 16, over. Now, guys, what I'm doing is the first term, root 6 times root 6, which is root 6 times 6. Then I'm going root 6 times 2. So that's 2 root 6. Negative 2 times root 6. So that's minus 2 root 6. And then negative 2 times 2. So the middle terms cancel. And that's why we're doing this. That's why we are multiplying it by the conjugate, because the middle terms will always cancel. So what you end up getting is 8 root 6, not 16, sorry, plus 16 over 6 minus 4, which, well, I'll write this down. So 6 minus 4, so 8 root 6 plus 16 over 2. Now, actually, so this is good, but you can still reduce this one more time, because now we can divide everything by 2. and get a nice and simple little answer. All right, cool. Let me just check the chat here. All right, so let's look at one more. There's not that many examples on this section, but let's look at one more that might be a little harder. And then we'll finish off with topic 25. So we're almost there. We're almost getting done, but let's do one more of these. I'll pick a hard one for practice. Okay, so like question number I. Oh, actually, question number I is going to be interesting. But let's do it. Let's do it anyways. So again, I see two terms on the bottom, and I'm going to multiply it by the conjugate. So I'm going to multiply it. Again, I only care about the bottom. So I'm going to multiply it by 3 root 3 plus 7 instead of 3 root 3 minus 7. Okay. So now what I'm going to do is, I guess the word would be simplify. It doesn't seem like we're really simplifying it, but I'm going to multiply the tops and the bottoms out. So for the top, my first term, I'm going to get 6 root 3 times 3. Then I'm going to get 14 root 3. So guys, I'm just multiplying this out. I just don't have enough room to write it every time. Then I'm going to get 3 root 7 times 3. And then my last terms, I'm going to get 7 times root 7.
Mr.
Yeah.
Plus 7 is plus root of 7, not plus 7 only.
For what one?
When we multiply in the opposite, the second thing, root of 7, not 7.
Yeah, you're right. Sorry, that's a bad mistake for me. That's a terrible mistake. So yeah, obviously this has to be root 7 because I have to copy down the exact opposite. And I was just, sometimes again, when you're talking, it's hard to, let me fix that. It's hard to like talk and write at the same time. All right, so let's just fix that there. But that's a good point. It needs to be root 7 for it to be the exact opposite. Okay, so let's see what we get here. Same thing here. I'm still going to get 6 root 3 times 3, right? Multiplying the first guy. Then I'm going to multiply the last guy. So I get 2 root 3 times 7. Okay, then I'm going to multiply the inside guys. So that would be 3 root 3 times 7 again. And then I'm going to get the last guys, which would just be root 7 times 7. So that's the top. This one is a hard one, by the way. I'm just doing this to show you. And now the bottom. So 3 root 3 times 3 root 3, that's just going to be 9 square root 3 times 3. 3 root 3 times 7, or root 7, would just be 3 root 3 times 7. Minus 7 times 3 root 3 would be minus 3 times 3 times 7. And then my last term would be minus root 7 times, 7. All right, simplify. Let's see what we get. So I'm going to get 6 times 3 plus 5 root 21 plus 7. I still need to simplify the top. If you're wondering where I got the 5 root 21, I just combined these two in the middle. And then here I'm going to get 9 times 3 minus 7. Okay, so simplifying this, 6 times 3 plus 7. I'll get 25 plus 5 root 21 over 9 times 3 minus 7 is 20. Okay, I could reduce this actually. So I could do one step further. I could divide everything by 5 for the final reduction. And there we go. That was a hard one. Woo! That was a challenging one. All right, so that's multiplying by the conjugate. All right, so we got one little topic left and then we're done for today. This is the last topic that'll be on your test. Tomorrow, obviously, we're not going to do anything new, but I'll be around in class time if you guys have any questions. The cool thing about this topic is, and you guys are going to like this on your test, is you can use your calculators for this. This is mostly calculator work. So this is kind of like an introduction to logarithms. We're going to, not today, not tomorrow, but after your test, we're going to go a little deeper into logarithms. They're actually pretty interesting.
Mr. The test will be include this the log 24, 25.
Yes.
There are 5 topics in it in 24.
No, there's only one topic in 25. It's topic 25. So logarithms we're going to use a lot, like when you guys go into chemistry or physics or any other future courses, you might talk about a logarithm. And a logarithm is basically a button on your calculator. We're going to look at logarithms and natural logarithms. So what a logarithm does is it takes something exponential and kind of reduces it down. So what's an exponent first? Well, we already talked about exponents a long time ago. An exponent would be like y equals something to the power of something. So an exponential function is something that has a variable in the exponent. And that's not really what we're talking about here today. I'm going to show you what a logarithm is. A logarithm is a way to rewrite what's called an exponential function. So you can see here in the red and the blue, there's a way to write this as a logarithm and a way to write this as an exponent or exponential. So the logarithmic form, x is equal to log lowercase b y, and the exponential form, y equals b to the power of x. So you can kind of see the similarities with these. Like if you look at this example here, 4 to the power of 3 equals 64. 4 times 4 times 4 is 64. Well, a logarithm has a way to rewrite that where we could say the log base 4, I don't know what I just did, something just popped up on my screen. Log base 4 of 64 is equal to 3. So we still have the same numbers here. We're just rewriting them. So let's look at how to do that. It says write each exponential function in logarithmic form. Well, 16 is equal to 4 squared. We know that. When I rewrite this as a logarithm, I would rewrite it. I would read 2 is the log base 4 of 16. So the 2 becomes equals the log, I take the 4, and this 16 goes here on the end. It's kind of like just rewriting what's already there. There's a reason for logarithms, by the way, but we'll get into that in the next topic. So what about b? 2 to the power of 5 is 32. Well, what we would say is 5 is the log base 2 of 32. What that means is we take the 5, and that goes equals. It's the same thing as before. So up in the top, let me just erase my writing. Here the 2 equals, here the 5 equals, and then we say log of this number, the 2, times 32. So we would say log base 2 of 32 is 5. Again, same thing, right? There's 4 examples here. So the -1 goes equals. Okay, -1 is the log base 5 of 1 over 5. So it's the same thing over and over and over. Let's do some practice of this, or for this, sorry. So like question number A. So 2 is the log base 5, 25. Right? All right, what about B? So B, 5 is the log base 3 of 243. Do you guys see what I'm doing there? Oh, I did the easy ones. Is there more practice? Not really. What about, well, I'll give you guys a minute. Why don't you try C? Don't get caught up with the negatives and fractions. Just kind of rewrite what was already there. The formula I can put on the bottom here. So if you had the exponential form y is b to the x, you would rewrite it as x, the exponent, is equal to log b y. So why don't you just take a minute and try question number C? Anybody get the answer? Oh,
Yes, sir.
Okay. I guess it's pretty hard to write in the chat. So again, there's not really anything to this. There's no solving this. The last part of this topic is putting this into your calculator. But what I would do is I would say, okay, well, -2 is the log base 3 of 1 over 9. All right, for D, well, I mean, there's so much more practice in this. So I guess I could do D. So D, we would say 3 over 5 is equal to log base 32 of 8. All right, so what if we go backwards? What if we go in the other direction? Write each logarithm in exponential form. Well, excuse me. Same thing as before, we're just going backwards. So 2 is the log base 3 of 9. I would rewrite that as 9 is 3 squared. The cool part about going this way is it's very easy to check your answers, but I'm going to show you in a minute how to check your answers anyways on your calculators. So 9 is obviously 3 squared. 2 to the power of 4 is 16, right? 7 to the power of -3 is equal to 1 over 343. So this is just going back and forth through logarithms to exponential form. 27 to the power of 1/3 equals 3. So how about instead of me doing this, why don't you guys practice this? I'll just write the formula here. So why don't you guys try the first two? Just try A and B, and I'll be back in a minute.
Sir,
Yes?
I want to ask about the last assignment, the grade.
Yeah?
When it will be uploaded.
Today.
Okay, thank you.
No problem. All right, so let's look at the answers for this, or for this question. Just give me 1 second here. Copy link. Okay, I'm sorry. Had to post something for my other class. Okay, so pretty straightforward. 5 squared is 25. What about B? So 5 cubed is 125. That's it. There's no calculating here, nothing to it. It's just rearranging these equations. 9 to the minus 2 is 1 over 81. 16 to the power of 1/4, which is interesting because we just did this, is 2. Just a little hint, that is the same thing as this. But you don't need to write that. But just a reminder of that's what we just did. Okay, so this isn't really the point. The point is, I mean, it's good to know how to rearrange or write logarithms, but that's not the point. The point is, how do you solve a logarithm? How do you do it in your calculator? And this is the best part, is that what I'm about to show you, this is the last part of topic 25, is how do you solve this? How do you put these things in your calculator? How do you get a number for this? So this is the last part. This is really easy because, again, this is literally, you cannot do this without a calculator. This is nothing to do like simplifying radicals in your head. This is just straight up calculator button. So if you guys have your Casio calculators with you, you can calculate logarithms by entering them in on your calculator. The book here is talking about a TI-84 calculator, a Texas Instruments. It's the same for a Casio. I think with the Casio, though, I don't know if I need to close the bracket. Nope. So you don't even need to do this on a Casio if you don't want to. Not for this question. So if, I don't know if you guys have your calculators with you, but to do these, very easy. You would just enter on your calculator log 500 and press equals. Your parents, when they did this, they would have probably used, like I know my parents are like in their 70s, they're pretty old. They use what's called a logarithm table or a book to do this. We don't have to, we can just enter them in on our calculator. So there's really not much to teach here. Maybe I'll give you guys one to try, but like, for example, for question A, I would just press on my calculator the log button. Oh, one thing I can show you real quick. Give me 1 second. Casio, yeah. I'll just show you guys where the log button is. Ah, there's a fly. Oh, I hate this. Hold on, guys. Open in new tab. Oh, actually, okay. Hold on. I'm going to share my screen here. I'll show you where the log button is. The log button, you can see I'm on Amazon, but you can see my screen. The log button is here. And actually, both of these we're going to talk about. So log and LN looks like the word in, but it's actually LN. So those are your log buttons on your calculator. So log of 900, just put this in on my calculator, hit equals 2.9542. It goes on for a while. You don't, it just says write it to 3 decimal places. Okay, what about B? Log of decimal 238. This is negative 0.6234. Oops, that's more decimal places than I need. All right, so again, very easy. Why don't you guys try C and D? So, did anybody get log 5 on their calculators? Should be pretty easy. Should only take you 2 seconds. 0.699. Log 1000. Ooh, that's a good one. 3. Again, I'm just using my calculator for this. So what about if you're given something else to solve? So okay, for this example, I'm saying log 5 equals 0.699, or I'm saying log 1000 equals 3. Well, what if I ask you log of what number will equal 1, 2, 3, 4, or log what number will equal 0.123, and so on? Well, to solve for this n, you would just use the second function of the logarithm on your calculator. The second function of the logarithm on your calculator is called the anti-logarithm, the anti-log. So if you get a question like this one where you're asked to find the n, this could be x, by the way, or n. Well, whoops, sorry. You would go second function log and then put in the number and hit equals. So it would look like this kind of on your Casio calculator. Okay, so like what about B? Log n equals 0.123. Well, I would press second function, or I guess for you guys, it would be shift log, put in my number, 0.123, and get my answer. Pretty straightforward. Right, same thing for this one. It doesn't matter if it's positive or negative. I would go again, shift logarithm, and then enter the number. And that's it. So for these questions, let's see. I'm going to go shift. I wish I could show you my calculator, but shift log 2.365. This would be 231.739. What about B, second function logarithm, 3.534. This would be 3419.794. Pretty straightforward. All right. So what about on your calculators? What would you do if you had a logarithm that was not normal, like it had a different base? What I mean is if you looked up at these examples here, where like back here, these examples, these logarithms have these different bases. So the problem with the log button on your calculator is that the log button on your calculator represents log 10. And I know this says TI-84, but it's the same thing for Casio. To enter a logarithm where the base is not equal to 10, meaning I can't just press the log button.
Mister, in the calculator, I can't do it without this divide. I can do it. There is bottom up to the line.
What?
It's log. Open your calculator.
Oh, yeah.
You will see. You can do it without.
You're right. So on the TI-84, you would have to enter the formula. But if you look at your new calculators, let me share my screen here. It's right in the top corner, right? Oops, hold on. Give me one sec, draw. Okay. It does that every time. Why are you doing that to me? I'm just trying to draw on my screen, but you can see it. Yeah, here we go. Right here. If you want to enter a logarithm with a different base, so if I wanted to solve, say, log 3 to 10, you can use this button on your calculator. That's right. Perfect. So that makes our lives even easier. You don't need to worry about the formula if you have a nice Casio calculator. We're almost done, by the way, guys. There's I'm just showing you how to use your calculators, and that's it. So if you look at these examples, if you don't have a Casio, in order to solve something like A, you would have to take the log of 560 and divide it by the log of 5. Or on the Casio, you could use your log button, and the log button looks like this. So yeah, I mean, this is, again, very easy. You just, these are worth marks on your test tomorrow, and all it is how to enter numbers in on your calculator. So like 2 minutes, I'll be done, guys. Log 5 to the 9. When I put this into my calculator, I will get 1.365. Okay, now what you could do is, again, to solve something like this, I could use my formula. What I mean is here, I could go log 5 over log 9, or just use the Casio calculator to solve this for you. So Casio calculator, log 9 and 5 gives me 0.732. Easy. Log 11 to 77. Like, this is hard to teach because I wish I could just show you what my calculator is saying. I'm literally just putting this in on my Casio. That's it. There's no way you could do this without a calculator. Please, guys, tomorrow come with a calculator. The last thing, this is it, the finale, is you might see a question tomorrow where instead of log, it says ln, ln. Well, ln is just like a logarithm, but it has a different base. It's called a natural logarithm. So if you see ln tomorrow, wink, wink, and I say, you know, solve ln of 50 or solve ln of 0.091, you don't use your log button, you use your ln button. And that's it. That's it for this topic. So let me just show you some of these examples just so you have some answers to look at, and then halas, we're done. I will show you C because you might not know how to put C in on your calculator. So the ln button on your calculator, if I can get my calculator open again. Oh, I hate this. Ah, hold on.
Shift the ln.
Yeah, ln is right next to log. Sorry, I'm just trying to get my screen shared. It's right here, ln. So if you see ln, instead of using log, use the ln button. But there's one thing I want to show you. In question C, there's something a little different. So let's look at A and B, and then I'll show you C. So ln of 500, don't press logarithm, press ln on your calculator, 500, you would get 6.214. Same thing for this one. Don't press logarithm, press ln, 0.325. That would be negative 1.124. This one, what's going on here? What is this E? Well, if you look on your calculator, it's above the ln button. So let me show you. This is the last question, by the way. Can you guys see that right above the ln? It's hard because my screen is moving, but you see a little written E. Oh man, I wish I could write on the screen. Okay, good. Woo. So see that little E? So if I had to enter ln E squared, I would just put this in on my calculator. I think it was E squared. It might have been 2E. So you would press your ln button, then you would press shift, then you would press your E button and put in the numbers. So for this last example here, I'm going to press ln, shift ln to get the E and put in a 2. And I get my answer of 2. And there's a reason that it's 2, but we'll talk about that another day. Woo! Okay. So guys, we're done. Halas, that's it. That's topic 20.
The ln delete the E.
What? Yeah, exactly. Yes. The ln kind of like deleted or removed the E. And there's something special about that that we'll look about a little later. All right, guys, that's it. So I'll be around today. I have a class now for another 2 hours or about an hour and a half. But I'll be around this afternoon or this evening if you guys can, send me an email if you have questions. And tomorrow morning, you don't actually have class at 9:30. So tomorrow at 9:30, I'll just be online. I'll be on Zoom if anybody wants to jump in and ask me a quick question, but there's no class tomorrow. And that's it. So if you guys have any questions, again, send me an email tonight or tomorrow or whenever, and I'll be around today.